have started recording the class on the cloud. Today, the outline of today's lecture. So, we will derive first negative binomial regressions. So today we are going to learn negative binomial regression. Okay. So what is negative binomial distribution? Negative binomial distribution. This is what we are going to learn. And then mean of negative binomial distribution. And then finally, we want to do some kind of gamma exponential mixture of negative binomial distributions. I will explain that. And finally, we want to derive negative binomial regression. These are the things. After that, we will do real life example. Real life example. Okay. Last class we discussed Poisson regression. Poisson regression, where mathematical form of the Poisson regression is this: x equal to x e to the power minus lambda, lambda to the power x over factorial x, and x takes value 0, 1, 2 up to infinity. Okay, this is called the Poisson distribution. And in last class, I mathematically derived this Poisson distribution from binomial distribution under two assumptions, where lambda is a parameter equal to NP. NP is the mean of the binomial distribution, and n has a characteristics, that means n tends to infinity. If n tends to infinity, probability of happening of an event is 0, that I mentioned, like in Macomb, Chandler Park, which is the busiest intersect. How many accident takes place in there? Maybe 100,000 car passes in whole 24 hours or more than that. So how many accident takes place? Very little. So this is what Poisson regression. In Poisson regression, we also discuss the mean of Poisson distribution equal to that, which is also equal to variance. Okay. So Poisson distribution has mean and variance equal to same. Okay. Poisson distribution has mean and variance equal to same. Okay. So suppose you have a count data. You have a count data, right? You have a count data. In this classroom, in this class, altogether 35 students, right? So 35 students, we have mother and mother sisters, right? Mother, sisters. If we consider all of our mothers and their sisters, and how many children are born from each of these women, we will get one woman give 3 births, another one 7 births, another one 9 births, right? Right. So this number of births, if you find the mean and variance, and if mean and variance are approximately same, mean and variance are approximately same. Of what? Mean and variance of the count variable. Count variable. What is the count variable? The count variable is number of children ever born number of children ever born from women of our moms and their sisters, right? So take a look at that. You must watch my video, so your questions will be like technical question as well as computational question in your exam. So for example, suppose in this classroom there are altogether 35 students, so at least we have a 35 moms. Okay, so and then their sister altogether, suppose we have altogether 500 women. So women 1, women 2, women 3, up to 500 women. These 500 women are our moms and their sister. That means aunts, right? So we can end up with number of children, children, children. Women 1, 2, women 3, 5, women 3, 7, women 4, 0, women 5, 11, and 500 women, she might have like just the 7 children. So these are the number of children, right? So this number of children I can put in the Python like data, and then I can put it here 2, 5, and 7 up until all. And then I can find the mean of these. So d dot mean, Python code, d dot mean and d dot variance. If we find these things, we will get mean and variance, right? If these mean and variance are equal, we have to use Poisson distribution. Clear? On the other hand, if these mean and variance are not same, mean of x is not equal to the variance of x, then we have to use negative binomial regression. Clear? Understand? Yes. So Poisson regression and negative binomial distribution will be used when your dependent variable is a count variable. That means you can count. Understand, right? Count data. There should not be any continuous data. Okay. So you understand where to use Poisson regression and where to use negative binomial regression. Now, if mean equal to variance, like not exactly equal, approximately equal, then you can use Poisson regression. If mean is not equal to variance, then you have to use negative binomial regression. Okay, clear, right? All of you in this classroom have seen this model, which is known as the linear model, right? Linear model, right? Regression model, this is multiple regression model. Now you want to know how can we formulate negative binomial regression. Like the way in last class, I have shown you how Poisson regression come into an existence, right? In this class, what you are learning the theory behind, how the theory works. This is what in the classroom I discuss. All the theoretical derivation I discuss, and then I discuss a real life applications, couple of, and then I discuss a real life applications, and in your homework, you just do the applied part, right? Understand, right? So now let us start. What is negative binomial distribution? Let us do now negative binomial distribution. Negative binomial distribution. Take a look. Here I have written binomial distribution. Here I have written negative binomial distribution. So binomial distributions probability format is this. This is what I have discussed you last time. P to the power x, q to the power n minus x, where n equal to number of trials, p equal to probability of success, q equal to probability of failure, q equal to probability of failure, x equal to number of successes. Here x takes value 0, 1, 2 up to n. This is the mathematical form. Okay. Mathematically, if I do these things, mathematical operation, we will get mean equal to expected value of x. Expected value of x if I write mean expected value of x equal to NP, variance of x equal to NPQ. Mathematically, we can derive these things, okay? So this is what. Ready? All of you ready? I'm going to show you distinction. How binomial distribution is different from negative binomial distribution. Your exam question will be also some conceptual questions will come in your exam. Understand? Conceptual questions will be in the exam. Ready, right? A family has 12 children. Probability of boy is 0.7. What is the chance that 7 of them are boys? Are you understanding the question? A family has 12 children. Probability of a boy is 70%. What is the probability that 7 of them are boys? So number of trial is fixed. Number of trials is fixed. So that means here I am writing number of trials is fixed. Trials is fixed. That means a family has how many boys? 12 boys, right? A hospital has 50 patients. Are you understanding? N equal to fixed. N equal to fixed. Understand? N equal to fixed. A hospital has 50 patients. Okay. A graduate class has 25 students. N equal to fixed. Number of trials. A coin is tossed 15 times. N equal to what? 15. Tossing one coin 15 times is exactly equal to tossing 15 coins one time. Understand? Tossing one coin 15 times is exactly equal to tossing 15 coins only one time. So number of trials is fixed. This value must be given. Before doing the experiment, this N value must be in your hand. Understand? That is the main concept, that in this number of trials, this and that will be distinguished. Understand? Now, probability of success is given. The probability of a boy is 70%. Probability of a patient as a COVID patient is 50%. The success probability must be given. Okay? And this is the number of success that we are looking for. Am I getting 0 success, 1 success, 2 success, 3 success? That is what is given. Clear, right? Now I am going to write negative binomial distribution. So negative binomial distribution, x equal to x, and then x plus r minus 1, c r minus 1, p to the power r, q to the power x, where x takes value 0, 1, 2 up to infinity. Any question? No question, right? Question? No question. You have a question? Look like you have a question.
Yeah,
Oh, the second, yeah, yeah. 14? It should be 21st. Why did I put 14 then? Okay. It will be 21st. Today is 14, right? Why didn't I put here 21st? Oh my goodness. Anyway. Okay. Take a look what I am writing. Okay. So now here x equal to what? Number of failures. Number of failures. Are you understanding?
First line is not.
Which line? First equation, this one?
Yes.
X plus beautiful R minus 1, C beautiful R minus 1.
Okay. Professor, the probability is X equals to what?
Here?
No, the probability.
Is here?
Yes.
Beautiful is small x.
Thank you.
My handwriting is not that bad, right? You know, when we were undergraduate students, so our professor, when they give us the problem, we write problem, they tease us the student. With this handwriting, if you born 40 years ago, and if you send a letter to women for marriage, you will end up with the rejections. You have to fix your handwriting. Understand? Here x equal to what? Number of failures. Huh? Okay? X equal to number of failures. R equal to number of successes. Okay? R equal to number of successes. And P equal to probability of success. P equal to probability of success. Okay. So now your question is, they look like same, but why one called the negative binomial distribution and another one is called the binomial distribution? How these distribution come into an existence? Clear, right? Let me give you an example. Ready? Everyone ready? This gentleman invited me, my wife, and my 2 daughters to his home. For what? For dinner. He invited me, my wife, and my 2 daughters for having dinner at his home. And he asked me, what do you like? I said, we like salmon fish very much. He said that, well, I will catch some salmon fish. Okay. So how many salmon fish? He decided to serve us 4 salmon fish. Okay. 4 salmon fishes he decided. He went to the river with the angler. How many fishes he has to catch? 4, right? So 4 times he will throw. He might get 4 success in 4 attempts, right? He might never get 1 success, right? Or after spending 3 hours, he get 3 success. But how many times he put his angler to the river? So in order to get that, listen, the data that is generated in the negative binomial distribution is different from the way data is generated from here. Here data is generated, all the number of trials is fixed. It is given at the very beginning. Here he does not know. Suppose this gentleman, and this girl, they 3 went to the river. He put his angler 15 times. He put his angler 25 times. She put her angler 9 times. Possibility, right? So negative binomial distribution, success data is generating failure, success, failure, failure, success, failure, 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 success. Are you understanding? Here data is generated 1 by 1, 1 by 1, 1 by 1. Clear, right? So once he got the 3 successes, that means he got these things. Once he got the 3 successes, so suppose he got 17 failure, 4 successes, 4 successes, minus 1, C, 4 minus 1. Okay. So among these, 17 failure and then 4 successes minus 1. So that means he got 3 successes in here, right? So take a look at that. 4 minus 1 equal to what? 3, right? So 70 is the fixed x, right? So then R equal to, I put here 4, but 4 minus 1, right? Now take a look at that. How many successes he got? 3, right? 3 successes. And how many failure he got? 17, right? And once he got the 4th successes, he is done, right? So that is why that is put separately. He will be done once he get the 4th fish, right? Are you understanding how this come into an existence? So this is exactly binomial. This is exactly binomial. But once he get the 4th success, he is done. Are you okay? So that's the way. If you write it beautifully, it should be written like that way. It should be written as x plus r minus 1 c r minus 1, and then p to the power this and that, it will be altogether 4. That means r, and then q to the power x. Let me again explain. His target is to get how many successes? 4 successes, right? So he got 4 successes, 3 successes he got, and then when he got the last success, that is why he is done. So that's the reason it is separated like that way. That's the way. This part is the completely binomial, because 17 minus 14, sorry, 17 plus 3 equal to 20, 20 C 3. So among 20 trials, he got 3 success, and when he last got that one is his 21st one. Are you understanding? See, 17 plus 3 equal to 20. Among 20 trials, he got 3 successes. When 21st trial got the success, he's done. Are you understanding? And why it is infinity? Because you do not know when you will get the number of 4 successes, right? You may stand there whole day, whole night. You might end up with no fishes, right? So if you went to the apple garden, you want to have 4 apple by stoning. Okay. So you are stoning, you do not know when you will get the 4th success. Okay. You understand? This crazy guy want to marry a girl. He is proposing and proposing and proposing until 7 acceptance. 7 girl now wanted to marry me. Understand? Do you understand? Most of the time in our life, we are happy with only 1 success, right? Do you believe in that? Only 1 job, only 1 good school admission, right? Right? So that follows also mathematical model that is known as the geometric probability model. Okay? I teach, if you next semester, if some of you take my business analytics course, I will teach all the probability model there. At least 10 probability model with real life example. Geometric distribution is one. So you understand the difference between them, right? So why they are called negative binomial distributions? This coefficient can be written in a negative format, which I am going to show now. And why it is infinity? Because you do not know when you will get your desired number of successes. Clear, right? You do not know. So that's why it is going on. So this is the derivation. This is the derivation. Okay. Now let me show you. Okay. This one has a mean expected value of x equal to RQ over P. And it has a variance of x equal to RQ over P square. Okay. The online student Eric and Vaishnavi, are you okay?
Yes, Professor. I'm good.
Okay.
Yes.
So now let me first of all, I explain you why in negative binomial distribution, the upper range of the number of failures is infinity, right? So you could end up with infinite number of failures and you would never get the desired number of fishes, right? So that is one. The another reason why they are called negative binomial regressions, let me show you. Here is the coefficient. Negative binomial regression coefficient is x plus r minus 1 c r minus 1. That is equal to minus r c x. These two are same. These two are the same. Now I'm going to show you these things and then I will derive this mean. Okay. So if in the left-hand side, if I write x plus r minus 1, c r minus 1, which could be written as x plus r minus 1 factorial, r minus 1 factorial, and then x factorial. It is just the x factorial x, which we could write by writing let me write it like this way. We can write it x plus r minus 1, x plus r minus 2, and then all the way if we go, x plus r minus x, and then we can write here x plus r minus x, and then minus 1. We can write like this way, and it should have it like this. So this x and that x cancel, and here r minus 1 we can write, here factorial x we can write. Now these things and that things cancelled out. Okay. Here we can also cancel out x and x, then it is r. So let me show you that right hand side is also the same thing. So right hand side minus r cx, which could be written as minus r factorial, and then x factorial, and then minus r minus x factorial. Minus r minus x factorial. So if we cancel this out, it should be just the r, right? So similarly, if we cancel that one is out, we would have here minus r minus 1, and all the way minus r minus x plus 1, and finally we will get minus r minus x factorial, which is equal to, in here factorial x minus r minus x factorial, these things and that things cancelled out. Okay, now if you take out all the minus 1, you will get exactly what is in the left hand side and right hand side. That's the way it is called also negative binomial distribution. Now I want to show you how negative binomial will have a mean equal to RQ over P. I will just show the mean. I'm not going to show you the how the variances one. And then there will be a format we have to develop in order to find this mean inside the mathematical model. And after deriving that things, then we will go for regression model. At the end, down the road, if I do not do these things, down the road, you can say that, well, we know linear regression equal to y equal to x beta plus epsilon. So how they consider here portion? So partial distribution, partial regression is come like that. They are original probability distributions, and in that original probability distributions, they plug the value and finally find the likelihood function. From there, they did just the first order, second order derivative to find the Hessian matrix, and finally Newton-Raphson method, the famous Newton-Raphson method. Okay. So now, if I want to derive these things, expected value of x could be written as sum x x plus r minus 1 cr minus 1 p to the power r and q to the power x, and x takes value 0 to infinity. This is the definition of expected value with respect to negative binomial distributions. So after this, x is a variable in here, p to the power r is a constant, there is no x. So we can write here x equal to 0 to infinity, and then x I wrote here, x plus r minus 1 factorial, and then here I write here r minus 1 factorial, and then here I write here factorial x and q to the power x. Okay, q to the power x. I'm finding the mean. Why mean is so important? Because in all regressions, we always take a loop, we always target mean changes, right? Unless it is a quantile regression, which we are going to learn. Like in a state of mean line, we are going to construct like regression line on different percentile values. So now, if it is written e to the power r, and then we want to bring a q from there, and we want to write here x equal to 1 to infinity, because 1x is cancelled out, and then here we have here we can write here r minus 1 x minus 1, and then x plus r minus 1, and then q to the power x minus 1. Are you seeing a x in there? If I take 1x out, that x and this x cancelled out. As 1x cancelled out, x jumps from 0 to 1. It is now starting from 1. 1x. If you do not change it 1, that means you're destroying everything. Okay? So after this, now we have a we have a we want to put these things now in this format. P to the power r, q p to the power r, sum x goes 1 to infinity. I want to put there r, and then I want to put here factorial r. I brought 1 r in there, I increase it by r. Brought 1 r here, I change it to the factorial r, and then I write it here x plus r minus 1 and so on. You have a question? Okay. Then q to the power x minus 1. So now you can put here rq p to the power r, and then now if you plug the value in there, x goes 1 to infinity. If you plug the value in here, then it will be again a series. A series could be written there like this: r cube to the power r, x plus r minus 1 and c r. It is written like that way, and then q to the power x minus 1. That quantity, that quantity can be written like that way, like this. Okay. Now, if we plug the values of x's, r cube p to the power r, if you plug the value, suppose I plug x equal to 1, then there is a 1. If I plug x equal to 2, then we will get r plus 1, x equal to 2, r plus 1, cr. then Q, and then if I plug X equal to 3, R plus 2, C, R, and Q square, all like this way, which could be written as R Q e to the power R 1 minus Q to the power 1 minus Q to the power minus R. RQ over P R plus 1. This is what. That series would be written like binomial series. If you just apply normal binomial formula, NC0, P to the power 0, Q to the power n minus 0, NC1, P to the power 1, Q to the power n minus 1. If you expand that thing by ignoring negative sign, do not bring negative sign at all in your head. Whatever value is in there, just plug like this way. You will end up with this series. Okay, you will end up with this series. And it is infinite series, it will go because the summation is in this format, so it will go like in that format. So here, if you put R, Q, P to the power R, 1 minus Q equal to P, 1 minus Q minus R, and minus 1, then you get RQ to the power P to the power minus 1, then finally you got RQ over P. So that is the derivation of the mean. So I have written negative binomial distributions mathematical format, and then I have given you the explanations how negative binomial distribution is different from binomial distribution. In what sense? Right? I have given you the rationale that last trial is a success, that means you are done. Okay? Last trial is a success, that means you are done, you got. And then I claim that this negative binomial distribution has a mean like this. This is the mean, RQ over P. That is the mean, which I mathematically derived from the distribution RQ over P. Where R equal to what? R equal to number of successes. You want to catch 4 fishes, and Q equal to probability of failure to catch a fish, and P equal to what? Probability of success. Okay. Now, next 1 hour, I am going to derive lot of mathematical things in order to convince you why existing mathematical model of negative binomial distribution is not appropriate for regression setting. Understand? Take a look. Poisson distribution has these things. Poisson distribution, probability of X equal to X. Okay. That capital X is the random variable. The specific small x is a value of that random variable. Understand? Can anyone of you tell me what is random variable? So what is the difference between variable and random variable? Age is a variable, right? Age is a variable, right? Age is a variable. Yes. So is it a random variable? What is the difference between variable and random variable?
Actually,
What?
actually, understand the age and
We cannot predict the outcome. It's other. If someone asks you this question, what is the difference? Let me go next page. What is the difference between variable and random variable. So what you said is exactly opposite. What you said. So random variable has a certain probability that runs with it. How? Take a look at that. Random variable is a mapping from sample space as a sample space to real line. Okay, what does that mean? So that means here you have a 3 coin tossing experiment: HH, HT, TH, TT, H and T. Here is 2 coin, here is 1 coin. So you have a HHH, HHT, HTH, HTT. There is a THH, THT, TTH, TTT. Understand? X equal to number of head. So X equal to what? 0 head, 1 head, 2 head, 3 head, right? Are you okay? So I said mapping. Mapping means also function. Random variable is a function. Function of what? Sample space to real line, right? Now take a look at that. X equal to, I put here head, head, head. So that means X equal to what? 3, right? 3 head, right? Now probability of X equal to 3 equal to what? 1 over 8, right? 1 over 8, right? So now if you put here X equal to 0 head, 1 head, 2 head, 3 head, probability of X equal to 1 over 8, 1 over 8, 3 over 8, and 3 over 8, right? Right? So now it is a sample space, and this X is a random variable. This is a sample space, and it is mapping to the real line 0, 1, 2, 3, 4, -1, -2, -3. So it is a mapping. So X is a function from sample space to real line. Are you understanding? Are you understanding or not? Random variable X. This is the X is a random variable. X equal to what? Number of heads. Number of heads of what? 3 coin tossing experiment. When you toss 3 coins, you will end up with one of these 8 sample points. So you will have 0 head, 1 head, 2 head, 3 head. So X is a function, X is a mapping from sample space to real line. So that means it will have a certain underneath hidden probability. Probability structure isn't there. But age may not, right? So if you take height, would it be a random variable? Yes, it will be random variable if it has a with certain probabilities is in there. So the variable and random variable main difference is that variable is a characteristics that vary person to person, circumstances to circumstances, time to time, places to places. Understand, that is variable. But what is random variable? Random variable is a function from sample space to real line. So that means it has a certain probability. Clear, right? So if someone asks you what is the difference between variable and random variable, that should be your answer. Just tell them random variable is a function from sample space to real line. So that means it has certain probability to happen. It has certain probability to happen. So that is why randomness is coming. When I discuss these things, this is called Poisson regression. Poisson regression has a very beautiful format because expected value of x equal to lambda. Understand? So in regression, what we focus? We focus on the average, right? In regression that you have learned y equal to beta 0 plus beta 1 x plus epsilon I. This y does what? You have a x value is in here and y is in here. This is your all values. This is your all values. And you fit a average line, right? It is average line, right? So Poisson regression, mathematical format has a beautiful lambda, that means average in its probability model. Are you understanding what I say? So this is the average, right? This is the average. Expected value of x equal to lambda, which I derived in last class, right? So Poisson distribution itself contains the average. Poisson distribution itself contains its average lambda. But negative binomial distribution x equal to x does not contain x plus r minus 1 c r minus 1 p to the power r q to the power x. It does not contain the parameter rq over p. Are you seeing rq over p exists there or not? No, right? No, right? rq over p is not in the negative binomial distribution, right? We have to conduct some operations on this model so that we can bring an average. Without bringing average in the model, how can I predict average? All the model, regression model, simple regression, multiple regression, logistic regression, probit regression, lasso regression, least regression, elastic net, those are for dimension reduction, and then Cox regression, linear mixed effect models, all of these models they discuss with the average change. Understand? They discuss with the average. Unfortunately, our negative binomial distribution does not contain average parameter. So we have to do some mathematical operation on this model in order to make that probability model in the format that the model will contain the average parameter. You understand? So this is the average line, 50% median line, 50% average line. All regression model, Poisson, negative binomial regression, all these two have a average parameter. But this one does not contain this formation. Okay. So we have to bring something in here. That is why next set of mathematical operation is needed. Okay. So now, in order to do that, we have to assume, I have written in my handwritten note very beautifully. We have to assume that in Poisson distributions, they have a hidden parameter and conditional distribution. So this is what yi and then xi comma tau I. This is a hidden parameter. On that parameter, I want to write it as a Poisson minus mu I tau I, and then mu I tau I to the power yi tau I divided by yi. This is what called Poisson distributions where parameter, hidden parameter tau I is in there. The original Poisson distribution looks like this. This is a with tau I as our hidden parameter. Okay, so this is a conditional distribution of yi given xi, which are our covariate, and then tau I. So now, marginal distribution, how can I find the marginal distributions from there? Marginal distributions of yi given xi. From there, if I want to find that one, we have to integrate out on the tau I, we have to integrate out yi, xi, comma tau I, and then d tau I. So you know this one, probability of A given B would be written as probability of A and B divided by probability of B, which is called the conditional probability. This is the definition of the conditional probability. So from there, we will apply something in here, probability of, if you multiply these two things, then you will end up with probability of A given B times probability of B equal to probability of A and B. So now if you multiply these things, yi given, this is a yi and tau I given xi. So from there, I want to write it xi given tau I f of tau I tau I. Now we have to assume there something. Tau I follow gamma distribution. Gamma distributions with theta comma theta with probability density function as f of tau I equal to theta to the power theta, like this, tau I theta minus 1 e to the power theta tau I tau I. We are assuming here this distribution follow gamma distribution. Okay, gamma distribution is a probability distribution. We have to use this in order to find our desired mathematical function. Have you heard the name this gamma distribution? Have you heard the gamma distribution? Okay, so that means you are not like fall from sky. You know some of this. So where this is 0 to infinity, I'm defining what does this gamma means. That is the definition. Okay, our forefather they defined those things. Gamma function, this theta, so gamma of 6 equal to actually factorial 5. Okay, so then x to the power theta minus 1 e to the power minus x and dx. This is the gamma function. That's the way gamma function is written. Why they did all of these things? Because Poisson distribution is easy, and then Poisson distribution has a condition mean and variance of the same, but negative binomial distribution mean and variance are not same. So the scientists they started thinking that, well, so let us do mathematical operation on that so that we can bring their mean parameter. Without mean parameter, you cannot fit the equation. That's the rationale they are doing. Okay, after plugging all of this value in there, we want to find this conditional distribution. So when all of those values are put there, e to the power minus mu I tau I to the power yi, and then here I want to put here yi, and then theta to the power theta, and then tau I to the power theta minus 1, and e to the power minus theta tau I. I want to integrate out tau I completely. Okay. So I have written all of these very details in the derivations. Very details. I have written all of these derivations in the note. If we do all of these operations and then gamma functions rule that I have written in here, gamma functions rule that we will end up with the final format by avoiding, I am avoiding 3 lines. I am avoiding 3 lines. Finally, we will end up with this yi plus theta, yi plus theta over yi factorial this theta plus mu I to the power theta and mu I to the power theta plus mu I divided by yi. Okay. In your, I have written handwritten derivations. I have uploaded a document, right? And written the derivation. If you look at, I avoided 3 lines. If I apply on that is gamma function, then it will come up like that way. Okay? Are you okay? Take a look at that. If it is P, then it is Q. How? If P equal to, because our negative binomial distribution is P to the power R, Q to the power X, right? If P equal to that, theta plus mu I, then Q equal to what? 1 minus P, 1 minus theta over theta plus mu I. So you are getting mu I over theta plus mu I. Are you seeing that? This is P, that is Q here. Right? Right? So we understand P and Q obtained. Now we have to prove these things equal to X plus R minus 1 C R, right? We have to prove these things. Now take a look at that. That one I can write gamma 7 equal to factorial 8, right? Sorry, factorial 6. Gamma 7 equal to factorial 6, right? Now that could be written as yi plus theta minus 1 factorial, right? This could be written as that factorial. That could be written as yi minus 1 factorial. That could be written as, this is written as y, sorry. It should be, this should be written as yi. That should be written as theta minus 1 factorial, right? So this could be written as yi plus theta minus 1 c theta minus 1. Are you understanding? So this is similar to the negative binomial distribution. Originally, negative binomial distribution was that one. Originally, negative binomial distribution x equal to x plus r minus 1 c r minus 1 p to the power r q to the power x. Now that one is this one. This one equal to p. That one equal to p. And that one equal to q. Okay. So you are convinced that this one is a negative binomial distribution. Now we have to convince you what? We have to convince you what is the mean of this. Let me write these things. Let me write these things. Mean equal to what? Mean equal to RQ over P, right? RQ over P. We want to check whether we are getting that quantity in there. So our case R equal to theta, R equal to theta in our case, this was R equal to theta, and Q equal to what? Q equal to that, which equal to mu I over theta plus mu I, and P equal to what? P equal to theta over theta over, we got what? Theta plus mu I. So this and that cancel, this and that cancel, we have a mu I. Are you okay or not? Are you okay or not? Are you okay or not?
Okay.
You are okay. So now you are saying mean this equal to mu I, that mu I now exists in there. Do you understand? That mu I now exists in there. Yeah. So we got our mu. So now we can now put our regression format in there. That is why this operation is done, because we want to bring mu, we want to bring mean directly in the mathematical format. So that's it. Now rest of the thing is just we can fit the regression model. You have a question? So all the talk that I did for last few minutes, we have a negative binomial distribution. We have a negative binomial distribution. That negative binomial distribution does not have the mean. And all regression has a purpose, is to fit an average line. Understand? That distribution does not have a mean in this format. By doing those operations, we brought mu is in there. We brought mu is in there. Mu is the mean. This is the distribution, but I have shown you RQ over P. If this is my R, this is my P. If I plug all of these value, I am ending up with mu I. So think few minutes how much efforts mathematicians and statisticians give to come up to manipulate the original distributions to this distribution. Do you understand? Okay, so our major part is done. So similarly, we have to prove there. We have to prove there, and then I will do the likelihood function. Then we are done. Then we will go for our programming and real life explanations. So mean equal to this, mean equal to RQ over P, and variance equal to RQ over P square, original. Okay, so as P lies between 0 and 1, in that case variance is greater than mean for negative binomial distributions. For negative binomial distribution. So we derive mean of the new negative binomial distribution is mu, which is existing now in the mathematical format. We have to also prove that there should have a variance formula, variance analytical format or mathematical format of the variance. We have to find that one, and we have to prove that variance is greater than this mu. We have derived something. We have to also convince that the variance of the new negative binomial distribution must be greater than the mean of the negative binomial distribution. So what is the variance? Let me write here. RQ over P square. RQ over P square, right? So let me put it in there, all of those values. R equal to theta and Q equal to mu I over theta plus mu I, and then p square equal to theta square, and then theta plus mu I square, p square, rq over p. So now we have in here mu, and here we have theta, then here we have theta plus mu I. So if we write like this mu, and then we have a theta, then we have a theta plus mu I. So now if you multiply this in here, you will get mu plus mu square theta. From here, if you compute this, mu over theta. This is the mean. This is the mean. Here always be I. Let me put there I so that you would not be confused. This is the mean, and this quantity is always greater than 1, right? This quantity is always greater than 1 because mu I are parameter, theta are the parameter which is always positive. If it will be negative, that means you are destroying everything. It can never be negative. So this is a positive quantity, and that is 1. So that means this variance is bigger than that one. So our condition from original negative binomial distributions, that quantity, that things is satisfied for the new distribution. Okay. So now let us derive likelihood function. Of the newly derived or derived negative binomial distribution. Okay. So likelihood function we can derive for only one observations, and after taking the log, if we take the summation on there and sum 1 to n, then it will be the likelihood function for the all observations. Okay. If I take only one observations I and then I just sum it over after taking the log, that will be the likelihood function. After taking likelihood function, we need to differentiate it first time and then second derivative, and then we have to use Newton-Raphson method. Okay. Yes. So this is the variance formula from the original negative binomial distribution. This one. Mu I over theta. Yeah. Mean is this. Mean equal to that. RQ over P. Okay. Let me again explain these things to you. This is our negative binomial distributions, right? That I discuss and make a comparison with the binomial distribution. What is the problem of this negative binomial distribution? It does not contain the mean parameter. That is the problem. So in order to overcome that problem, we have done some mathematical operations, which is known as the combination of exponential Poisson mixture of Poisson random variable, gamma mixture of Poisson distribution, gamma mixture of Poisson random variable. Where gamma mixture? consider here tau I as a gamma. Why they are considering these things? In order to make a new negative binomial distribution that will contain the mean parameter. After doing all of these things, I got this. I got this distribution, which I say that this is my new negative binomial distribution. Now, in this new negative binomial distribution, didn't I say that this is my P and this is my Q? And then I showed that if P equal to that, Q equal to automatically this. Okay. So in this case, now if someone find expected value of this, someone find expected value of yi given xi, he will find mean mu I. This is what I said in here. RQ over P was the original mean. Now R equal to this theta, R equal to this theta, R equal to that theta, and this is my P, this is my P, and that is my Q. When I plug these things, I got the mu. Mu is the mean which exists on these negative binomial distributions. That is what we need. And after getting the mu, now we have to find the variance. That is the variance formula. That is the variance formula for the original negative binomial distribution. So this is the original negative binomial distributions. I plug the value of R, I plug the value of Q and P square. I end up with these things. And I have shown that this is my variance now. That variance quantity is bigger than this mean quantity. Originally, this is bigger than that. If you plug any value of R, P and Q, plug it in there. But that value should be rational. R is the number of successes. Number of success could be 1, 2, or 3. If you plug R equal to 0, then going mean and variance both of this 0, then there is no negative binomial distribution. You went to fishing to catch 4 fishes, you did not get any success. That means R equal to 0. Then negative binomial distribution does not exist. So that is a trivial case, R equal to 0. All other positive values of R, where R equal to 1, 2, 3, and P and Q are any rational value between 0 and 1. If you plug this in here, this is always greater than that one.
So, when you get the strike value of means and variance,
so this is the original formula, right? In this formula, and that is the derived one, right? That is the derived one. Now, if you want to find these things, you are said that no, professor, I don't believe you. You said that no, professor, I don't believe you. I want you to beautifully derive these things. Yi given, what was that? Xi. I want you beautifully derive these things. Then what I should do? Just I will write this and f of yi given xi and then probability of yi. Then what I will do? Here 0 to infinity, I will just plug y and then I will plug that value that I just derived in there. This value I just plug in there and just use the gamma distributions formula, and finally I will end up with very beautiful mu. So I did not do another derivations in here. This is just the application of gamma distribution. Okay. So, okay. What is the end, like at the end, what we learn? We learn negative binomial distribution does not have the mean parameter. We have to bring here mean parameter. Understand? And we have mathematically proved these things. So if these things could not be done, then what is the option? Suppose there is no way, no mathematical operations, no like mixture of the gamma mixture of the Poisson variable, nothing like that. Then what is the solution? Solution would be numerical solution. There are many computations things. They are For example, any function, if I give you, can you integrate that analytically? Suppose if I give you these things, integrate these things. F of x equal to e to the power 5x plus sine x cube over 9 divided by log of 20x plus e to the power x. Integrate this from 0 to 9. Is there any closed integration? Closed form means you will find at the end, you will find very beautiful result that this is equal to 3x. So we are going like this. That is called the analytical form, analytical solution, theoretical solution. So what will happen if this is the scenario? You will go and write some code, Python R or MATLAB code, and then they will give you numerical result. Now, if you go for like higher study, PhD, now many cases, they have some kind of very ugly mathematical format, but they do not know any analytical solution. Understand? So this beautiful operation, if does not work, then there should have a numerical solution, writing code, writing program. Okay, you got the point, right? So your question was about like how this mean and how it is yeah. So I prove these things, mean and variance equal to that, and that is when I plug the value in there, mean value, I plug this value, I got the mu I, and mean variance value, I plug all of this, I got variance equal to that, and then I have shown that this one is bigger than that one because original distributions, that one is bigger than this one. So now, rest of the thing is just find the likelihood function. Likelihood function on what? Likelihood function on this. Likelihood function on that. Because in that likelihood function, in that distributions, we have a mu. On that mu, we can write like this. On that mu I, we can write like e to the power x beta. So then we said that, well, e to the power x beta is now you are considering in mu parameter. Okay. So, or you can do log of mu I equal to x beta, and then mu I equal to e to the power x beta. Did you get it? Because now this mu can consider a combination of covariates with the parameter. That is the mean of the distribution. Clear, right? Okay. So now likelihood function of one observations, you can write this. Likelihood function, you can write, this could be written as f of yi given xi, which could be written as yi plus theta, like this, and yi and theta. And then theta plus mu I to the power theta, mu I, theta plus mu I equal to y. See, I have written likelihood function from in the derived format. The derived format I have written this one. So in this case, now we want to plug yi plus alpha, because let theta equal to 1 over alpha, and then it could be written as alpha inverse and then factorial y, y plus 1, and then I can write it like this. Then 1 over 1 plus alpha mu I Anyone has a question in the back? Alpha minus 1, alpha mu I, 1 plus alpha mu I to the power yi. Then if here log is taken, L, that means log of L is taken, then we have a n, I goes on to n, ln, this is like this, yi plus ln minus ln yi plus 1 minus, I can write here alpha inverse ln 1 plus alpha I yi minus yi ln 1 plus alpha r alpha mu I plus yi ln alpha plus yi ln mu I. So one formula, this is available. This things has been used. ln yi plus these things can be written like that. With this quantity, we can write finally n yi plus after that we cannot go any further. What we need to do? Just the first and second derivative. First and second derivative will give us the Hessian matrix or Hessian matrix. Hessian matrix, remember I discussed Newton-Raphson method. After that, we have to find log of L, log beta. Now you can ask me question, why did you get the beta? Beta means this mu I, if you plug this mu I equal to e to the power x beta, then x beta will have all of those x's and mu's. You understand, right? Mu is the mean, right? That mu should contain, I will plug all mu's should contain beta and x. You can ask me a question, you are differentiating these with respect to beta, but I do not see any beta in there. Beta will be in here. This mu I will be replaced by the betas, and then finally differentiation. First order derivative and then second order derivative, beta I, and beta k. And then with these things, you will get a Hessian matrix and solutions, but finally Newton-Raphson method. Raphson method. So when you write a scientific paper, if you do any research or any thesis, In your thesis, you are writing or you are using negative binomial regression and Poisson regression. One paragraph you have to explain this theoretical model as well. Developed by someone else, but you have to explain in your paper that how did you do all this. But if you go to the top university for the PhD, during your PhD, you have to develop some model. Otherwise, the people will come from external university. Okay. First question they will ask you, what is new in here? What have you developed in here? This is the first question, like the top school, top 20, top 30 school, if you'll go there. And first round of questions, second round of questions, third round of questions. Sometimes that questioning will last around 2 hours, 3 hours. Questions after questions, okay? So some talented people, they develop those things. Our responsibility is to study, understand, and apply to real life. Clear, right? So I will start discussing practical thing, but let us have a 5 minutes break, okay? Let us have a 5 minutes break. After the break, I will go to the application part, R code. We will run those things. Eric and Vaishnav, do you have any question? Are you understanding?
I don't have any questions.
Okay, so few students are outside. So tomorrow there is a workshop on causal inference. Do you know about that? In Quad City?
Yes.
So are you attending? Are you attending? Anyone attending? There is a workshop on causal inference tomorrow in the Quad City. The student can attend that workshop by $10. I think it will be reimbursed. If you attend that day-long workshop, you will learn new statistical methods on the causal inference. You can write in your resume and they will give you free breakfast and free lunch. For a student, it is $10. You don't know about that? Yes, sir. Are anyone attending? Yes. Okay. So still there is a time, if someone of you are interested, you can join, you can like make a group of 4 or 5 people, go there and then contact with the department director, they will reimburse him. Okay. What? I don't know. Maybe Zoom option is also available. Ask. Anna, you know Dr. Anna Velava? Anna Velava, ask her. Okay. Dr. Anna Velava, ask her if you can join by Zoom. It will start 8:30 and will end at 4:30. You can write in your CV that you attended a workshop on causal inference, and then it will enrich your CV. Okay. Okay. Take a look. Next week, we are going to learn these things. We are going to learn Ridge regression. Ridge regression. We are going to learn lasso. That means dimension reduction. So people say high dimensional data, high dimensional data. Those things you are going to learn in here. Dimension reduction. Ridge regression, lasso regression, dimension reduction, and then elastic net. Elastic net. This is also a combination of Ridge and lasso. This and that, the penalty that are using in here, the penalty that are using here, these two penalty are added in there. They call it as a elastic net. What does this mean? If you have a 100 variable, are you going to use all the variable? How do you know all of these things? You do not know the importance of all of the variable, right? Previously, people use stepwise, stage-wise regressions, but 1996, this lasso was developed and 2007, elastic net was developed. Those problems can be answered by using this. If anyone tell you, I have a lot of data, lot of variable, how can I handle those things? Elastic net or lasso regression. This is what we are going to learn in the next class. I will mathematically derive and then I will give you real life example, okay? Understand, right? High dimensional data. How can I do dimension reductions? This is the answer. We are going to learn these things. Clear, right? You understand? I raised my voice. Why? So that you can listen. Okay, now let me go to the materials that I have uploaded in their course content. So homework, let me download these things. It is anymore. I don't know what happened. So let me go and open the document. Handwritten. Okay. So this is the negative binomial regression. We have to understand these things. Actually, you have to understand these things. Read each line of this document. I did not give a lot of documents, just 2 documents. One reading from Poisson regression, another reading from negative binomial regressions. And whatever we have done in here, you have to write a report like this from this real life example data. You have to create something like this and you have to give explanations that is mentioned in there. Okay, so this data is a data where independent variable are the math score and the type of the programs, and dependent variable is the number of days the students absence. So number of days is a count data, right? In the entire academic year, number of students absence from their class, that is the count data. What they have derived first here, they derived here basic statistics like the mean, standard deviations, all of these. Then they have computed some count that like the bar chart for each of these program. For general program, the count is like this, and then for academic program, count is higher. It went up to 20, and for vocational one, count is way higher. This goes to maybe 40 up to 40, and this is the overall results. The last one, we got the overall result. So in this case, we want to predict like from the math score and the types of the academics about the number of days absence. Okay, so let's go there. The data has a 314 variables. I did not download this. Let me download that one from there. Here is the R code. Okay. And if you feel comfortable, you can also do the same thing by using Python. Python and R are the only options you can do this thing. Okay. If you do not understand this code, do not know how to run this code, do not know, then there will be a problem in your exam, which is coming, which will be in class exam. I will give you data. Within the data, I will ask you some questions. Take this variable, do these things, operation fast on that variable, and then use this as your dependent variable. Clear, right? Okay. You have a question? You can use Jupyter. Jupyter is better. Actually, your homework, I see, one student submitted the result in the Jupyter. With the all output is in there. I like Jupyter. Jupyter, if you submit, that's fine. So let me download this code. Are you seeing PR and NBR code? So download that code. I downloaded that code. Let me open it. NB data, right? So now let me see. I have to download that data as well. Download that data. Now go to the download folder. That data. Just copy this. Here, control V. R. So that is the summary statistics we got. And then we are creating GG plot. GG plot is not found, could not find GG plot in there. So I need to run the package as well. So go back to here, GG plot. Think that will- So you have to change in this code. Use data you will put, use variable you will put, and that results will be different because I have given freedom. I did not specify what variable you will choose. Understand? You have to choose. So each student's results will be different. Okay. So the questions that I said that you choose the variable, you put this, then your results will be different from people to students. Okay. To run this, we will get this result, and this is the parameter estimates are obtained. So the probability model that is used in here, negative binomial distributions, because we put here ZLN.NB, and this stands for negative binomial. ZLN.NB. Go back to that document that we have provided in there. If someone will ask you this question, have you heard the Gaussian regression model? You said yes. Do you know how to use it? His answer is the data is counted. Then if they will ask you, have you heard the name zero inflated Poisson distribution? You understand? Someone asks you, have you heard the name negative binomial regression? You said yes, negative binomial regression can be used when response variable is a count data and mean and variance are not equal. Variance is greater than. If they will further ask you, have you heard the name zero inflated negative binomial distributions? Then what would be your answer? Do you understand? Just without running these things, I am telling you some words. Don't know what happened. I cannot write it in there. I don't know what happened. I have to restart this thing, but I'm not. Okay. Please pay your attention to my words, what I'm saying. If from now to the rest of your life, someone will ask you what is negative binomial regression and what is Poisson regression, you can answer. Poisson regression will be for the count data when that count data has the same mean and variance. Negative binomial regressions will be on the count data when variance is greater than mean. Clear? If now someone asks you what is zero inflated Poisson distribution, what is zero inflated negative binomial distribution, if these questions are asked to you, what will be the answer? You will say that in the data, if there is lot of zero appears, then for the zero and non-zero, we feed a model, and that model could be logistic model or probit model. And we, in addition to that, we will fit also Poisson regression model. Do you understand what I said? Okay, so suppose I said the 500 women, right? Our mothers and their sisters. How many women are together? 500 women, right? So 500 women produce offspring, children, right? So out of 500, suppose 250 produce 0 children. Isn't it lot of zeros? Isn't it lot of zeros? Out of 500 women, 250 women produce 0 children. So that means there are 250 zeros. Are you understanding? Real life example, right? So that means in your data, it is zero inflated data, right? Zero inflated data, right? So how can you fit this model? In this case, if you fit the Poisson or negative binomial regression, that result could not be stable, right? That is called the zero inflated. Can you answer this question to the audiences? If someone asks you, you just give explanations of Poisson regression model, negative binomial regression model. Do you know anything about zero inflated Poisson regression model or zero inflated negative binomial regression model? So that means in your data, lot of zero appears. That means lot of zero events. That means lot of mom would not have a children. Lot of the time there is no accident. Lot of the time there is zero accident. So in your data, lot of zeros. Understand? So in such a cases, zero and non-zero, you will feed logistic regression or probit regression. Zero and non-zeros. And as usual, you will also feed a Poisson regression. So two separate results will come. Understand? So if someone say zero inflated, that means in your data lot of zero appearing, and then you are fitting two different types of model. One for the as usual Poisson regression or negative binomial regression. Another one is zero and non-zero logistic regression or probit regression. Logistic regression and probit regression I will teach in business analytics class next semester. Some of you already know this, right? You know, right? Logistic regression and probit regression. But you also know, right? So I already, because the business analytics class 500, I already taught that. So next semester I'm teaching that. Business analytics, predictive modeling, as well as data mining. In data mining, I am teaching machine learning models. So everyone got it, right? So do not fall from the sky if someone says zero inflated Poisson regression model. Okay. So now let me go for the explanation of this. Here, it is mentioned zero inflated regression model. If this is what, if you see, that is just I just explained to you. Okay. And last time I said to read Poisson regressions documents that I gave, and also this is a negative binomial regression. With your cool temperament, read all of these documents thoroughly. So when you write your report, then you just copy the results from there. What they have said, you just write those things in your report. Understand? You will run the Poisson regression and negative binomial regression for a new data, but the variables will be different for you. All of your variables should not be the same. That is why I mentioned. And then when you write the report, how to write the report, you have to copy it from there. Clear, right? Okay. So now let me give explanations for this. So when you write the report, first of all, you can write the report in terms of parameter change values as well as incidence rate ratio, which is just taking the exponentiation. Both of these things has been mentioned in here. For example, take a look at that. Here R first displays the call and the deviance residuals. Next, we see the regression coefficient for each of the variables along with standard errors, z-score and p-values. The variable math has a coefficient of this, which is statistically significant. This means that for each 1 unit increase in math, the expected log count of the number of days absent decrease by that. So that means this is a negative. That is why the word decrease in here. So that means if this unit is increased, 1 unit increase, the predicted value of absence will decrease like that way. So that means the students who are very good in the math, they usually do not be absent from the class. Are you understanding? That is the way this explanation would be given. So it is said the variable math has a coefficient this, which is statistically significant. This means that for each unit increase in math, the expected log count number of days absent decreases by that. Now come to the other explanations, but this same explanation in the down part, they explain same thing again in terms of incidence rate ratio. Okay, the indicator variable shown as prob academic is the expected difference is in log count between group 2 and the reference group. So there are 3 groups in there. One is called vocational, another one is called the academic, and then another one is known as general. So general has been put as a reference category. General has been put as a reference category. Remaining 2 has have been put as a like comparison category. Comparison category remaining 2 have been put. So now take a look at that. The indicator variable shown and as program academic is the expected differences in log count between group 2 and the reference group. The expected log count for level 2 of program is 0.44 lower than the expected log count for level 1. Indicator variable for program vocational is the expected difference in log count between group 3 and the reference group. The expected log count for group 3 of program is 1.28 lower, which is very rational like this from the general one. Expected log count for level 1. To determine if program itself overall is statistically significant, we can compare a model with and without program. And then again, next time it is come from there, they also mentioned in here whether the overall model significance which can be obtained by the IK informations criteria. And then the 2 degrees of freedom of chi-square test indicate that program is a statistically significant predictor for day SAPs because there are 3 different categories. They are finding here. Whether like for these 3 categories the program is significant or not. So the theta parameter is shown in dispersion parameter. Again, you have to make a decisions from this median. If median equal to 0, then what? Can anyone tell me from last class? The assumption is satisfied, right? What assumption is satisfied? Could someone of you open that one? If median equal to 0, then what will happen? Reading peer. Median equal to this in the portion 1. Take a look at that, what it is said. From your median, you have to make a comment like this. When you turn in your report, you have to comment like that way. What is in there? The output begins with echoing the function call. The information on deviance residual is displayed next. Deviance residuals are approximately normally distributed if the model is specified correctly. In our example, it shows a little bit of skewness since the median is not equal to 0. Your median is not equal to 0. So in your output, when you get the median like this, you have to make a comment, one line of comment. Clear, right? So in our case, yes. P value of what? In here?
Yes.
So if P value less than 0.5, P value less than 0.5, in this case, P value less than 0.5, this is not. So that means program vocational is not significant. And that one, math is significant. You are talking about NBR or PR? Partial regression or negative binomial regression? Which one you are talking?
Yeah.
PR. So PR here, program vocationally is found to be not significant, right? Then it is typo. Where it is said. The output will. I did not find it. Where is it?
Yeah, just, yeah, after the.
In this line?
Yeah.
Oh, you do not understand this one? Okay. So take a look at what they said. That is in the model one, right? That is one in the model. In this case, it is found to be not significant in here. Is it a PR one? Let's see that one. In this case, it is not found to be that one. Now, what they are doing in this part, that is the chi-square. For what they are doing, they are checking number of absent for 3 different categories they are checking. In that case, they found that this is insignificant. So these are the 2 different things. In the model one thing, and the chi-square test is another thing. Chi-square test is telling you are talking about this one, right?
Yes.
Okay, now see what they are doing. We can also test the overall effect of program by comparing the deviance of the full model with the deviance of the model excluding the program. The 2-degree freedom of chi-square test indicate that program taken together is a significant predictor for the number of errors. What they have done in here, so degrees of freedom definition, if there are 3 categories, it reduces to 3 minus 1 equal to 2. So each of these 3 categories, they are comparing like the mean of the number of absence. So online people, I cannot write here, but I have to write something. Let me try one more time. I don't know what happened. Access power. Are you saying there is a cross sign? I do not know. I cannot cancel this thing. So that's the reason. So Control F4, alter F4. There is a way to cancel these things. It gone now? So now let me see. Okay. So what they are doing is 0, mu1 equal to mu2 equal to mu3. Okay. Each one at least one equality does not I never had this type of experience before. I never had this type of experience before. Okay, thank you for asking this question. She is asking why there. So H0, like they are doing this type of things. 3 program category, right? Mean number of absent for first program equal to mean number of absent corresponding to second program equal to mean number of absent for the third program. General program, vocational program, and academic program, right? And corresponding to these 3 programs, they are testing whether the average number of absent are same for each of the 3 categories. And what is the alternative hypothesis? Alternative hypothesis is this: at least one equality does not hold. That test could be done by the chi-square test. And then chi-square test with the 3 category, 2 degrees of freedom, p-value is very small. So that is p-value is very small. That is why they are rejecting the null hypothesis that equality of the mean number of absent corresponding to 3 different educational category. That null hypothesis is rejected. Understand now? This is known as the equality of several means. Equality of several means. Thank you for asking this question. I was able to ignore this. So then after this, now you have to explain same things in terms of incidence rate ratio. We might be interested in looking in the incidence rate ratio rather than coefficients. Incidence rate ratio. To do this, we can exponentiate our model coefficients. If it is done in terms of exponentiation, the parameter, then it will have a name incidence rate ratio. In your homework report, when you submit, if you just do the output of Poisson regression and negative binomial regression and say this parameter are significant, that is not enough. You have to also mention that chi-square testings and parameter must be explained, parameter estimates must be explained by incidence rate ratio, which is nothing but just the exponentiation of the parameter. You understand? Okay. So exponentiation of this parameter, let me ask you another question then. What is exponentiation? This is x, right? This is over x, right? How this value is defined? So e to the power x, our forefather just give a definition like this. It is just like that. 1 plus x over factorial x, x square over factorial 2, x cube over factorial 3, and then it will go all out. This is just the definition. Understand? That's the definition. So then if you plug e to the power 1, then it should be 1 over factorial 1, 1 square over factorial 2, 1 cube over factorial 3. If you put equal to 2, then 1 plus 2 over factorial 1, 2 square over factorial 2, like this. This is just the definitions. They have defined it like that way. Exponentiation. Yes. And then if you plug here minus, then it is minus, it is plus, it is minus, it is plus. Okay. So remember, sometime it is come to your head, it is just a series, it is the definitions defined by our forefather. So nowadays calculator and computer is available after 1970s. Texas Instrument first brought this calculator, and then 80s Casio brought all of these things. But before that, there was a book. In that book, there was all exponentials value was computed by plugging the value in there. British government, their Royal Mathematical and Statistical Society, they give lot of money, lot of human beings are employed, and they computed all of these things together and published a book. Before 1970, all universities around the world, they use that exponentiation book. The binomial probability that we just write the code and get in there. Before that, we have a binomial book. Understand? We have a log book. So I personally saw that, but now it is disappeared. Understand? Yeah, right? Okay. So this is the exponentiation series. So the incidence rate ratio, what they do, they just plug the value of the parameter estimate on the exponentiations. They got this. Okay. Now, what is this? They said log of E. So log of E means that E. Okay. So now, what is the definition of the log? This is the basic thing. So it is the definition of the log. E to the power x equal to y. E to the power x equal to y. Then we defined what? Log of y. Then we put here a equal to x. That is real life example. Are you saying this? Log, right? So 2 to the power 5. 2 to the power 5 equal to what? 32, right? So now log 2 to the power 32 equal to 5. So usually the 10 base log and exponential base log, these are the things used. This is the definition. This is the way our forefather defined. So if you want to say that, no, I want to do something different log. So what do you want to do? Suppose you want to do 3 to the power 4. 3 to the power 4 equal to 81, right? 3 to the power 4 equal to 81, right? So now if you want to do log 3 to the power 81 equal to 4. That is the log definition. Okay. So my daughter, she is now in the 3rd grade, but in the summer I was teaching her. She now knows how to do like system of linear equations, 2 equations, 3 equations, quadratic. She can now. So let me tell you one secret. Down the road, when you become parents, just give them time and politely and beautiful word, all beautiful word, all beautiful. Oh my goodness, it was so smart. I do not know how can you think all of these things. Beautiful word, and all the time talk, like give her very encouraging thing, and then she will start doing. She in the summer, in the May, June, she finished like 2 equations, 3 equations, quadratic equations, and then I taught her logarithms. I said that this is the definition, that's the way it's coming. So if parents give the time to their children, children will automatically be talented. You understand what I said? From my experiences I'm sharing with you. Down the road, if you If you have like these things, just always and never ever, entire life, never speak lie to the children. Never speak lie to the children. So I told my two daughters, my eldest one, on the planet, your best friend is your parents. And your dad, he has the highest degree, right? Your dad has lot of knowledge. Lot of knowledge. I said that whatever happened to you in your school, please come and tell me. Each time you tell me whatever happened, I'll give you a gift, whatever you want. Okay? Then she came to dad for the first time. She's not third grade. I saw in my desk some slips written, do you want to be my girlfriend? Do you want to be my girl? I didn't say to her, oh my goodness, thank you, you shared with me. Okay, so what do you want? So let us have a Dairy Queen. And then I was telling her, I'm very happy. Your best friend on the planet is your dad. You know, when you were born, you were sleeping, but I was not sleeping. Why? Because whole day you are sleeping, at night you do not want to sleep. You just want to play. Okay? That your mom is tired, but I have to take care of you. So you cannot believe how much time your mom and I gave. So all the best things in this planet we want for you. Then I said that tomorrow when you will go to your teacher and tell your teacher that these things happen. But make sure that nobody else listen. So that she to tell her teacher these things happen. Her teacher said that, well, I saw that yesterday you have done these things and that thing. Whoever did it, you must not do this. And then I said to her, did you do these things? Yes. Well, what did your teacher say? Teacher said, teacher give the warning to everyone, nobody should do that. The next time if anyone will do, then teacher will find check the handwriting, something like that. So how to raise the kids, the best approach is to give them time. Okay, sometimes they will be super mad. They need these things, they need these things. Today I said that, today if I will not get the ice cream, I will not going home. And then she also ganged up with her little sister. Yes, we will not go home. So, okay, let's go. So then I bought the things for them. So sometimes whatever they want, even I am a parent, I'm 100% right. I have to quit my right sometimes. And then after giving those things, then I convince my daughter, see, I listen to you. Are you going to listen to me now? So, okay, let's do something. So let's do some problem, some reading, something. She is second grade finishing, but I am teaching her the book in the high level. So you don't need to understand anything. You just practice the reading, just reading. Understand? So why I am saying these things? I am, when my daughter will ask me why you need these things, why they are doing log thing. There is a log is the word given by our forefather. Down the road, you will understand. Because of what? Big numbers is coming. So suppose if I put here US economy in trillion dollar number, and if we plot these things, that plot will not make any sense, right? But $1 trillion will be very small number. At least if we take the log after log, double log if I take, it will be very small. Then I can easily make it small, right? So that's when she was asking me why log is in there, big number is so problem. I said, big number, let me write a trillion. How many zeros? How many space is taken? So now if you use the log, are you saying, I gave the same example to her. I gave the same example to, so now it's become. So who did these things? Our forefather. They are very intelligent. They make the life very simple for us. Understand? So if you do not have any questions, I'm going to stop in here. Next class, 3 models I'm going to discuss quickly. Lasso, and then elastic net and ridge regressions. Okay, they are derivations and real life example. And then I'll give you the homework. So I'm going to stop in here.